the cylindrical coordinate system. In order to understand the cylindrical coordinate system, we consider the rectangular coordinate system, and we know that there are three axes in the rectangular coordinate system: the x-axis, the y-axis, and the z-axis. And then we consider a three-dimensional point in the rectangular coordinate system. We assume that the x, y, and z coordinate of this point are known. Let us draw this three-dimensional point in the rectangular coordinate system. So we consider the x coordinate of this point along x-axis, the y coordinate of this point parallel to y-axis, and the z coordinate of this point parallel to z-axis. Thus we get this point with the help of x, y, and z coordinates. So in order to draw this point in the rectangular coordinate system, we consider the x coordinate along x-axis, the y coordinate parallel to y-axis, and the z coordinate parallel to z-axis, and thus we get this point which is in the rectangular coordinate system. Now we are going to represent the same point with the help of cylindrical coordinates. And the three coordinates of this cylindrical point are rho, phi, and z. So we are going to find out the location of the same point with the help of these three cylindrical coordinates. The cylindrical coordinates are rho, phi, and z. So in order to draw this point with the help of these three cylindrical coordinates, we draw a line rho which is in the z is equal to 0 plane, and this line makes an angle phi with respect to x-axis. So we draw this line rho in the z is equal to 0 plane such that this line makes an angle of phi with respect to x-axis. And then we draw a line parallel to z-axis such that the length of this line is equal to the z coordinate of the point under observation, and thus we reach this point P with the help of these three coordinates, and these three coordinates are known as the cylindrical coordinates. So if we want to represent this point in the cylindrical coordinate system, we need to know rho. Rho is the length of this line in the z is equal to 0 plane, and this line makes an angle phi with respect to x-axis, and then we draw this line which is parallel to z-axis, and the length of this line will be equal to the z coordinate of the point under observation. So this is how we draw a point in the cylindrical coordinate system. Keep it in your mind that rho is the radial line which is in the z is equal to 0 plane, and this radial line rho makes an angle phi with respect to x-axis. So you guys can find out the location of this radial line rho. You guys can find out the location of this radial line rho in the z is equal to 0 plane with the help of this angle phi. And then you guys can draw the second line which is parallel to z-axis, and the length of this coordinate, this z coordinate, will be equal to the z coordinate of the point under observation. So the location of rho depends upon this angle phi. If phi is 0, rho will be along x-axis. If phi is 90 degree, rho will be along y-axis. If phi is 180 degree, then rho will be along negative x-axis, and so on. So the location of this point depends upon the location of this line rho depends upon the angle phi. Okay, so let us consider diagram number 30. In diagram number 13, we have considered our x-axis over here and our y-axis over here. And you see the radial line rho makes an angle phi with respect to x-axis. So you see this is a right angle triangle. The base of the triangle is x, the perpendicular of this triangle is y, and the hypotenuse of this right angle triangle is rho. So definitely x will be equal to rho cos phi, and y will be equal to rho sin phi, and z will be equal to z. So you guys can find out x in terms of rho and phi. X will be equal to rho cos phi, y will be equal to rho sin phi, and z will be equal to z. So you see, if the cylindrical coordinates of a point are known, what are the cylindrical coordinates? Rho, phi, and z. So if the cylindrical coordinates of a point are known, you guys can find out the rectangular coordinates of this point, and the rectangular coordinates are x, y, and z. So x will be equal to rho cos phi, y will be equal to rho sin phi, and z will be equal to z. Similarly, if x, y, and z are known, you guys can find out the cylindrical coordinates of this point. You guys can find out rho, phi, and z. And you see, how can we find out, you see, rho, phi, and z? We consider this right angle triangle. This is a right angle triangle. Rho is the hypotenuse of this right angle triangle, and we apply Pythagoras theorem to this right angle triangle. So according to the Pythagoras theorem, the hypotenuse of this right angle triangle, which is rho, will be equal to under root x square plus y square. And if you look at this right angle triangle, phi will be equal to tangent inverse y by x. And we know that z in the cylindrical coordinate system will be equal to z in the rectangular coordinate system. So this is a common, z is a common coordinate. Z in the rectangular coordinate system will be equal to z in the cylindrical coordinate system. So we can find out xyz in terms of rho phi z. Similarly, we can find out rho phi z in terms of xyz, and these are the equations which are used to transform a point from the rectangular coordinate system into cylindrical coordinate system, and a point from the cylindrical coordinate system to rectangular coordinate system. Now we talk about the unit vectors of a cylindrical coordinate system. So there are three unit vectors in the cylindrical coordinate system: the unit vector a rho, the unit vector a phi, and the unit vector az. These three unit vectors are normal to one another. They are mutually orthogonal. So these three unit vectors are normal to one another. You guys need to find out the location of these three unit vectors in the cylindrical coordinate system. So if you guys want to find out the location of these three unit vectors in the cylindrical coordinate system, you see the first unit vector a rho will be along the radial line rho, and we know that this radial line rho is in the z is equal to 0 plane, and this makes an angle of phi with respect to x-axis. So a rho, this unit vector a rho, is in the z is equal to 0 plane, and this unit vector makes an angle of phi with respect to x-axis. So the unit vector a rho is in the z is equal to 0 plane, and this unit vector makes an angle of phi with respect to x-axis. Similarly, the second unit vector a phi is in the z is equal to 0 plane as well. So a phi is in the z is equal to 0 plane, and this unit vector makes an angle of 90 plus phi with respect to x-axis. So the two unit vectors a rho and a phi are in the z is equal to 0 plane. These two unit vectors are normal to each other, but the unit vector a rho makes an angle phi with respect to x-axis, and the unit vector a phi makes an angle of 90 plus phi with respect to x-axis. And then the unit vector az will be along z-axis. In other words, the unit vector az will be normal to the plane containing a rho and a phi. So the unit vector az will be normal to the plane containing a rho and a phi. So basically, the location of these two unit vectors depends upon the angle phi. In order to understand the location of these three unit vectors, let us consider two simple examples. So let us consider this particular example. In this particular example, we assume that phi is 0. So if phi is 0, then the radial line rho will be along x-axis. If the radial line rho is along x-axis, definitely the unit vector a rho will be along x-axis. So in this particular case, a rho will be equal to ax, because a rho makes an angle of phi with respect to x-axis, and phi is 0, so definitely a rho will be along x-axis. We know that the unit vector a phi makes an angle of 90 plus phi with respect to x-axis. As phi is 0, so a phi will make an angle of 90 degree with respect to x-axis, so a phi will be along y-axis, and a phi will be equal to a y in this particular case. So a row will be equal to ax and a phi will be equal to ay and az will be equal to az will be along z axis. So if phi is 0, we are in the rectangular coordinate system because the unit vector a row is ax, the unit vector a phi is ay, and the unit vector az is az, and these are the three unit vectors of the rectangular coordinate system as well. So what I want to say that the location of the two unit vectors a row and a phi depends upon the angle phi. If phi is 0, a row will be along x-axis, a phi will be along y-axis, and az will be along z-axis. Let us consider another example. In this numerical example, phi is 90 degree. If phi is 90 degree, then we know that the radial line rho makes an angle of phi with respect to x-axis. So the radial line rho will make an angle of 90 degree with respect to x-axis, and we also know that the unit vector a row is along the radial line rho, so a row will be along y-axis. The unit vector a row makes an angle of 90 degree with respect to x-axis, so a row will be along x-axis. And we know that the unit vector a phi makes an angle of 90 plus phi with respect to x-axis. So 90 plus 90 is 180 degree. It means that the unit vector a phi will make an angle of 180 degree with respect to x-axis. If this unit vector a phi makes an angle of 180 degree with respect to x-axis, definitely this unit vector will be along negative x-axis. And the unit vector az will be along z-axis. So in this particular case, a row is along y-axis. I mean to say that this unit vector is equal to ay. A phi is along negative x-axis, so the unit vector a phi is equal to minus ax, and the unit vector az will be equal to az. So what I want to explain at this particular point, I want to explain that the location of the two unit vectors a row and a phi depends upon the angle phi. If phi is 0, the location of these two unit vectors will be different. If phi is 45, the location will be different. If phi is 90 degree, the location will be different. If phi is 180 degree, the location will be different. So you guys need to know the location of these two unit vectors in the cylindrical coordinate system, and the third unit vector, which is az, will always be along z-axis. You know that a row dot a row will be equal to 1, a phi dot a phi will be equal to 1, and az dot az will be equal to 1. A row dot a phi will be 0, a row dot az will be equal to 0, and a phi dot az will be equal to 0. Similarly, a row cross a row results in 0, a phi cross a phi results in 0, and az cross az results in 0. Now we are going to explain the cross product of these unit vectors. If you guys want to find out the proper direction of the resultant unit vector, you guys need to apply the right hand rule. So A rho cross A phi results in AZ. A phi cross AZ results in A rho. AZ cross A rho results in A phi. If we change the location of these two unit vectors, the resultant unit vector will change. A phi cross A rho will be equal to minus AZ. AZ cross A phi will be equal to minus A rho. And A rho cross AZ will be equal to minus A phi. So you guys need to understand the cross product of these unit vectors. These unit vectors are the unit vectors of the cylindrical coordinate system. You guys can apply the right hand rule and you guys can find out the direction of the resultant unit vector very easily. A three-dimensional vector in the cylindrical coordinate system will have three components. This three-dimensional vector will have a component along the unit vector A rho, another component along the unit vector A phi, and another component along the unit vector AZ. And this is how we represent a three-dimensional vector in the cylindrical coordinate system. So a three-dimensional vector in the cylindrical coordinate system will be equal to A rho plus A phi plus AZ. So this is how we represent a three-dimensional vector in the cylindrical coordinate system. The addition of factors. The addition of factors in cylindrical coordinate system is not a simple mathematical process. If you guys want to add two vectors directly in the cylindrical coordinate system as we did in the rectangular coordinate system, you guys need to satisfy a condition. And the condition is that this angle should be same for these two vectors. If the angle phi is same for vector A and B, then we can add these two vectors directly in the cylindrical coordinate system as we did in the rectangular coordinate system. Otherwise, we will have to transform these vectors from the cylindrical coordinate system into rectangular coordinate system. We shall add these two vectors in the rectangular coordinate system and we shall transform the resultant vector back to the cylindrical coordinate system. So we cannot add two vectors directly in the cylindrical coordinate system if phi is different for A and different for B. We can add them if phi is same for vector A and same for vector B. Let's say phi is 90 degree for vector A and phi is 90 degree for vector B. Then we can add these two vectors directly in the cylindrical coordinate system. So we need to satisfy this condition for the addition of these two vectors. So we know that the addition of two or more than two vectors results in a new vector quantity. And the addition obeys commutative law. You guys can change the order of these two vectors. The resultant vector does not change. So we can add these two vectors directly in the cylindrical coordinate system if phi is the same for vector A and B. So the component of the resultant vector which is in the direction of the unit vector A rho will be equal to A rho plus B rho. The component of the resultant vector which will be in the direction of the unit vector A phi will be equal to A phi plus B phi. The component of the resultant vector which will be in the direction of the unit vector AZ will be equal to AZ plus BZ. So this is how we add two or more than two vectors directly in the cylindrical coordinate system. The scalar product of the two vectors in the cylindrical coordinate system. So we need to satisfy the same condition for the scalar product as well. If phi is the same for vector A and B, then we can find out the scalar product of these two vectors directly in the cylindrical coordinate system as we did in the rectangular coordinate system. If phi is different for A and different for B, then raise your hands. You guys are stuck. You guys cannot find out the scalar product of these two vectors directly in the cylindrical coordinate system, what you guys will have to do under this particular condition, you guys will have to transform these vectors from the cylindrical coordinate system into rectangular coordinate system. You guys will have to calculate the scalar product of the two vectors in the rectangular coordinate system, and we know that the scalar product results in a scalar quantity, right? So the scalar product results in a scalar quantity, and the scalar product obeys commutative law. A dot B will be equal to B dot A. So let's say phi is 45 degree for A and 45 degree for B. If this condition is satisfied, then we can find out the the scalar product of these two vectors directly in the cylindrical coordinate system, and the scalar product is given in equation number 21. The scalar product will be equal to A rho B rho plus A phi B phi plus AZ BZ, and you guys can simplify this scalar product with the help of the scalar product of the unit vectors of the cylindrical coordinate system. We know that A rho dot A rho is 1. I'm talking about the unit vectors. A rho dot A rho, A rho dot A rho is 1. A phi dot A phi is 1. AZ dot AZ is 1. A rho dot A phi is 0. A phi dot AZ is 0. And A phi dot A rho dot AZ is 0, and so on. Let's say that we have got two vectors. These two vectors are equal in magnitude and they are in the same direction. Let's say A is equal to B. We have this particular condition that A is equal to B. So if A is equal to B, then A dot A will be equal to A rho into A rho plus A phi into A phi plus AZ into AZ. So A dot A will be equal to A rho square plus A phi square plus AZ square, and we know that the magnitude of vector A is basically equal to under root A dot A, and under root A dot A will be equal to under root the square of the rho component of this vector plus the square of the phi component of this vector plus the square of the z component of this vector. So we use equation number 22 to find out the magnitude of a three-dimensional vector in the cylindrical coordinate system. Let us talk about the cross product. So if we want to calculate the cross product of two vectors in the cylindrical coordinate system, we will have to satisfy this condition. We will have to satisfy this condition. Phi must be equal to if phi is 180 degree for A, then phi must be 180 degree for B. If phi remains the same for these two vectors, we can find out the cross product of the two vectors directly in the cylindrical coordinate system. And if phi is different for A and different for B, then we are stuck. We cannot find out the cross product of the two vectors directly in the cylindrical coordinate system. We will have to transform the vectors from cylindrical coordinate system into rectangular coordinate system. We will find out the cross product in the rectangular coordinate system, and we know that the cross product results in a vector quantity, so we will have to transform the resultant vector from the rectangular coordinate system back into the cylindrical coordinate system, which is really a very difficult job, right? So we assume that this angle phi is the same for A and B, so we can calculate A cross B with the help of this determinant, and we can calculate B cross A with the help of this particular determinant. We know that the cross product does not obey commutative law. We know that A cross B is equal to minus B cross A. Now in the cylindrical coordinate system, we assume that our three-dimensional space is in the form of a right circular cylinder. You guys can see cylinder in figure number 17. The radius of the cylinder is rho and the axis of the cylinder is z axis. So you see rho is perpendicular to z-axis. Rho is the radius of this particular cylinder. It is always normal to the axis of the cylinder. The axis of this cylinder in this particular diagram is z-axis. Let us talk about the limits of the three coordinates of the cylindrical coordinate system. So rho extends from 0 to infinity degree, phi extends from 0 to 2 phi, and z extends from minus infinity to plus infinity. We will talk about the spherical coordinate system in the upcoming class.